Okay, so this is chapter 4 about spectroscopy. Alright, so this is a rather short chapter, but this is really just to give you a synopsis of what well, it says it all here. But basically, spectroscopy allows us to figure out what objects in space are made of. Okay, so that's and of course we use what are called the spectral lines when we break light into its different components. Usually nowadays, of course, we use what's called diffraction grating. In the old days, they used to use prisms, so we can tell what type of atoms a particular object is made of. We can even, to some extent, tell what molecules are there. The big thing, of course, is the hydrogen atom. Hydrogen, the simplest element in the universe, actually turns out to be what the universe is mostly made of, that the stars are mostly made of hydrogen. Alright, so, it varies slightly from star to star depending on how old they are, but we'll briefly talk about the photoelectric effect. This is something that Einstein actually explained, and of course, the analysis looking at the spectral lines. So, the last chapter we learned about the spectra, so this let's take a look at this picture right here. Of course, so this is your typical spectroscope. Again, you don't really use a prism nowadays. We use what's called diffraction grating. Anyhow, the light passes through the thing that, whatever it is, either a prism or diffraction grating, and splits the light up into all its different components. Alright, so these are just the visible ones. Obviously, there are other, well, not obviously, but there are other ones, right? There's stuff in the infrared and also in the ultraviolet, and further, right, the entire electromagnetic spectrum. Of course, you need special equipment to look like into the X-rays and so forth. All right, so what we're going to deal with is really, mostly what happens in the visible part of the spectrum. Keep in mind that this happens in all parts of the electromagnetic spectrum. But for example, if you have something like an incandescent bulb, a light bulb that is just hot and emitting light, it'll actually produce all the colors of the spectrum, like all the colors of the rainbow, the visible spectrum, I should say, and that is called a continuous spectrum, right? So that's important. If we heat a certain type of gas, as it's shown right here, what happens is as we heat the gas, the electrons in the gas get excited, and then they drop down to they can only be excited for a short amount of time, and then they'll drop back down to a lower state. And when they do that, they'll actually emit only certain colors of light, and they're kind of showing you this over here on the screen. So hydrogen has 4 lines in the visible part of the spectrum. They're well known, have been known for a very, very long time, since the 1860s, as a matter of fact. All right, so they're showing us some of the various various hydrogen or the various lines for putting different types of gases into a discharge tube and observing that discharge tube, observing the spectra of that discharge tube. So here are the lines, the traditional lines of hydrogen. It depends on how good your diffraction grating is that when you're looking at it. So this is actually only showing the 3 lines in the so this is the red line. This is kind of an aqua line, and then there's a purple line. And this is actually outside of the visible part of the spectrum. Here, let's see if does it show you that. Yeah. So anything beyond 400 nanometers. So this is 400 nanometers down here. These parts right here cannot be seen with the naked eye, right? So, because they're outside of the visible range. Humans can only see from 700 nanometers to 400 nanometers. So, and anything in between these two, that's of course what comes about, or what we can see. All right. So anyhow, there's actually another line in over here for hydrogen, but if you have a pretty good diffraction grating, you can see that, as I mentioned that just a minute ago. Here's the next one. There's only 2 lines for sodium, right? This one, of course, is very, very famous. Helium. Now, why is it called helium? Because when physicists and astronomers, physicists first, started to look at physicists and astronomers did a line spectra of the sun, they got a line spectra that they could not identify on Earth. Remember, this is going back to the 1860s. Hydrogen, of course, you could get hydrogen gas into a tube, and you can you look at the sun and you get the hydrogen spectra, and then you get hydrogen glowing. That is basically they put voltage across it, and you get these exact same lines. Okay, so that's a really important idea. Same thing with the sodium, same thing with neon, same thing with mercury. Gaseous mercury. But this one they could not identify on the Earth at first, and since it was only found this particular pattern, and that's going to become very important to us. These patterns, the one for whatever the element this happened to be, they only found it in the sun, and so they used the word for sun. And so they called it helium, right? And that's helios is after the Greek name for the sun. All right, so that was our discovery of helium. Of course, nowadays we can certainly we can find helium on the Earth. It actually, a lot of it comes from radioactive decay, which they didn't know about in the 1860s. All right, so again, this is the important part about this is this pattern of lines is only related to hydrogen. This pattern is only it's like fingerprints, right? It's exactly like fingerprints. No two fingerprints are exactly the same. No 2 emission spectra are exactly the same. And by the way, absorption spectrum looks exactly like this, but the lines are missing, right? The lines are missing right in these spots, right? For the red, for the aqua, and for the blue, and so forth. For any of these things, we'll get to what that means. Absorption spectrum, and I guess that's the next one. All right, so. If you have light, all the continuous wavelengths passing through, this emits a continuous spectrum, and it passes through cooler gas. What happens is that cooler gas will absorb some of the energy, and it depends on what that gas is made of. But if that gas, for example, if that gas is hydrogen, you're going to be missing this line, and this line, the red, the aqua, and the blue. And the same thing goes for any of the elements, right? It depends on what this gas is. But, whatever this cool gas is. And so you'll be missing some of these line spectra. All right, so there's another picture of it. Let's see, what is this? This is, looks like neon. It's exactly the same. For absorption spectra, the lines are there, but they're basically missing because those particular wavelengths have been absorbed by the there it says sodium have been absorbed by the cool gas, which in this case right here happens to be sodium. All right, so again, these are, you know, the line spectra, whether it's line spectra or emission spectra, we can tell what material is in the gas. All right, so this is dealing with what's called Kirchhoff's laws for spectral lines. There's actually Kirchhoff's laws for electricity and you know, for circuits. So that this is not that particular law. If you've ever heard of Kirchhoff's laws for, you know, when you do the anyhow, it's for voltage, current, and resistance. That's not what this particular one is. This is all about the laws for spectral lines, and so so I mean, we'll just read it off. So when you have solids or liquids or dense gas, they produce a continuous spectrum, low density hot gas. So if the gas is hot enough to emit light, you'll get an emission spectrum. And then for continuous, you have a continuous spectrum behind some cool gas, relatively thin. So in that, you know, that depends on what you call dense and what you call, very thin or very low density gas. Anyhow, if you do that, you get what's called an absorption spectrum. So, you know, if the gas is low density enough, you'll get an absorption spectrum, basically. So, so that's the idea of Kirchhoff's laws. All right, so yeah, and so they're showing it all right here. So here is a continuous, a source of continuous spectra, and then, you know, of course, just passing that through your diffraction grating or prism, you're going to get continuous spectrum. If it goes through a cloud of low density gas, you're going to get an absorption spectrum. And then, of course, if it goes through thicker gas, they're not distinguishing this here, but if in this direction, it goes through thick enough gas. Well, if the gas is hot enough, I guess I should say, if the gas is hot enough by itself, it will emit an emission spectrum. Okay, so that's the idea here. There. All right. So why do these lines come about? It really has to do with the arrangement of electrons in a particular atom. All right. So and sometimes that's called electron configuration. I should mention that as well. So different atoms, hydrogen, helium, the entire periodic table has the electrons in different energy states. And in fact, the ground state, what's called the ground state, the lowest energy state for an electron in an atom. Now, this is actually not a great looking picture nowadays. We use what's called quantum mechanics, and so the electron is not like in orbit around the proton the way we think of a planet orbiting its star, right? That's not the situation. The electron exists in more of what's called a cloud, and exists at a certain distance, and really that distance has to do with probabilities. That's getting more into quantum mechanics than I wanted to go, but anyhow, what happens is the electron usually through thermal energy finds itself into a higher state or an excited state, and when it does that, it'll drop back down to the ground state. All right, and so that's, in fact, that's what an emission spectrum is. The electron's in a higher state, it drops back down to a lower state. It doesn't always drop right back down to the ground state. Sometimes it goes in stages. It'll go to a very, very high state and then drop to an intermediate state, and then ultimately it'll drop down to the ground state. And it has to drop to the ground state. That turns out to be very, very important. well, not important. It always happens. It's like a ball up a hill. It always goes down to the bottom of the hill. It has to roll down to the bottom of the hill.